All right, settle down and get your seats. So my name is Janet Vertesi. I'm at Princeton University. I'm delighted to welcome you today to the panel on Mars exploration. The planet Mars has fascinated astronomers and space scientists for generations, to say nothing of historians, and this particular sociologist as well. And the papers in this session are focusing on the red planet, but they each display very different approaches to the history of Mars exploration. And each of these approaches reveals some of the contingencies and temporalities of this exploration work. We'll hear first from Richard Zurek, who's the chief scientist for the Mars program at JPL. Focusing on the missions, Zurek will take us through the trajectory of Mars exploration and its understanding from Percival Lowell to Curiosity. Such an approach will show us how each successive mission builds upon the successes and critical questions of the prior mission and how our knowledge of Mars is built up over time. Next, we'll hear from David Grinspoon, curator of astrobiology at the Denver Museum for Nature and Science. David will take the science point of view, specifically looking at the growth and change of the astrobiology community and its questions throughout this period of Mars exploration. And this kind of approach can tell us more about the concept of habitability, how it has been historically understood, and with what kinds of implications for the kind of science that is done. JPL historian Eric Conway focuses more on the engineering side, specifically engineering for a single mission, the much belabored Mars sample return. And those of you at the meeting in Germany earlier this year will know that that is a topic very dear to my heart as well. In this way, Eric Conway will definitely show us how a group of engineers at JPL were on the front lines of trying to implement shifting declarations from Complex, from the Space Science Board, and even the president himself, which reveals the complexities on the ground of being caught in the middle of 30 years of NASA crossfire. Finally, Henry Lambright, professor of public administration and international affairs and political science at the University of Syracuse, will take an individual approach. Focusing on the role and contributions of different NASA administrators, Lambright reveals the importance of leadership, complexities of decision-making, and the critical role of individuals in pushing forward the vision of Mars exploration. As a final note before we begin, as an ethnographer working with contemporary planetary exploration missions, these four histories continue to resonate throughout space exploration today. And the past is very much with us in the present. This is not just as a form of curiosity, no pun intended, but as the past moments of budget crises and bold visions show us, the concerns of our predecessors are very much our concerns today. And there are lessons here for how they chose to resolve those questions that can help us to address our own historical moment and our challenges. But perhaps more profoundly, their choices shaped in a foundational way the kinds of spacecraft we fly and the kinds of science that we do today. And that's one of the things that brings work on Earth and work on Mars ever closer together and continues to inspire our enthusiasm for Mars exploration today. So with that, I'd like to start by welcoming Richard Zurek to the podium. Chief Scientist for the Mars program at the Jet Propulsion Laboratory. Dr. Zurek's PhD is in the atmospheric sciences. He specializes in the atmospheres of Earth and Mars. He served as project scientist for Mars Surveyor 1998 missions, Mars Climate Orbiter, and Mars Polar Lander. He's worked with data from Mariner and from Viking, has led atmospheric advisory groups to support aerobraking engineering for our current generation of Mars orbiters, and is presently the project scientist for the Extraordinary Mars Reconnaissance Orbiter.
Well, what I hope to do today is to trace through space exploration, but also before that, the persistent themes that have made us interested in Mars, and to show you that in many ways those themes still drive us today as to what we want to do at the red planet. However, our concept of what Mars is and what it may be has certainly changed over that time. So just very briefly, if I go to the first slide here, here's what I'll try to talk about, those persistent themes. And I'll start going back to what I'll call the Percival Lowell view of Mars. And then we'll talk about the two waves of Mars exploration. You've already heard about the lost decade, which is what separates that first wave, where we flew by, we went into orbit, and then with Viking we landed. And then in the second wave of exploration, we've got more of an orbiter-lander synergy and added a new element that you heard about earlier too, which is mobility on the surface. And we'll talk about how that has helped advance what we do at the planet. Ending up with an idea about what Mars is today, but also I need to caution you that that story is very much unfolding at this very moment. We have two orbiters plus the Mars Express European orbiter active at the planet. We still have the Opportunity rover working on the surface, and of course Curiosity has now arrived to join them with its own expedition of things. So, to begin, those dominant themes. Mars is a place that we think has changed enormously over time, that it was very different in its early history, and it is now a different planet than it was in that early time. The geologic evolution of the planet has certainly changed. Over its history, giant volcanoes have built up. There are places in erosion on the planet. In some places, the wind has acted for 1 billion years in a way that we don't really have any terrestrial analog for. So there are processes, and this is what the planets give us, are these natural laboratories to be able to understand processes. But of course, a key thing with Mars has always been whether or not life is on the planet today, or it had been in the past, whether or not there is evidence of that past life that might be preserved today. And that's certainly something that we've been looking for in our space exploration of Mars. So let's begin, well, not really from the beginning, but at least let's go back 100 years, and let's talk about what the view of Mars was then on those 3 themes. Percival Lowell thought that he had a simple explanation for what Mars was. It fit all of the observational data that he had at hand, and he was responsible for accumulating more information about the red planet in a more systematic way. In fact, he coined the term planetology in a way that was actually a great debate at the time, because he was accused of being very selective about what things he took from geological studies of the Earth about how the Earth had evolved and such. And that's because his simple idea is that Mars was just an older version of the Earth. Mars and Earth have many similarities. They rotate about the same period, so their days are about the same. The temperature contrast between night and day are moderated because of that. Rotation axis of both planets are tipped over about 25 degrees. That means there are seasons. It's a warm summer pole and a cold winter pole on the planet there. So those similarities, plus the fact that Mars was all land, in fact about the same land area as the land area of the Earth, and the fact that both had atmospheres in which the sunlight went to the surface and could power not only the atmospheric circulation, but would be available as energy to life forms on the surface. Now, there was something exceptional about Mars in Lowell's view, and that was the canals. He and other observers saw the canals. They saw them in different forms. Some were very large and fuzzy markings on the planet that they drew. Others were, as Lowell drew them, were very straight and geometric that were indicating that, hey, there's more than just life on the planet. There's actually intelligent life on the planet. We've come a long way from that time, but even if you go to the mid-century here, that is into the 60s, when Mariner 4 was being launched and we were about to embark upon our space exploration, it is amazing how strong those ideas were and how we continue to debate them. In fact, there was a Mars handbook that was published by NASA in the late 60s, 70 cents, by the way, a real bargain for a student at the time. That handbook still wouldn't dismiss the possibility of canals, even though Mariner 4 had already taken its pictures and they were still being analyzed. The resolution of those pictures was not quite adequate to completely rule out what might still be on the surface of Mars. And in fact, our space exploration can be thought of as a desire to go to ever higher spatial resolutions to be able to see the fine detail that could actually help us test key theories about the planet. So this was Percival Lowell's view of the planet, and it had polar caps. Mars had polar caps. It had dark areas. One argument that the dark areas could only be explained by life was the fact that they changed color with the seasons. And in fact, they even reappeared after dust storms had brightened those areas, and the areas got dark again. And what else except vegetation would be able to do that? So trying to understand those kinds of mysteries has also been about what we're about. Now, by the 60s, the Earth-based measurements were also getting better, and there were some signs that Mars wasn't nearly as hospitable an environment for life as Percival Lowell had thought many decades earlier. The atmosphere was getting thinner. Well, our idea of the atmosphere was that it was not nearly as thick as we had thought it had been. And there were also better techniques in the imagery and the photographic photographs that were taken through telescopes and such that called into question the very idea that the canals existed. Mariner 4 successfully launches. I might remind you that Mariner 3 was the first attempt. In the same launch opportunity, the shroud didn't separate. It went into the ocean. They figured out the problem. They diagnosed it. They fixed it. Mariner 4 was launched in the same launch opportunity. We're talking about a period of several weeks here. I doubt we could get the failure review board together in these days to respond in such a way. And that was a sign of the experimentation of the times, the risk they were willing to take, and just the excitement and the drive of getting things done. Okay, so that first wave of space exploration, Mariner 4, Mariner 6 and 7, flybys. We're just seeing bits of the planet. Mariner 4, the images went across 1% of the planet at fairly coarse resolution, over 100 kilometers per pixel in most cases. Mariner 9, first spacecraft from Earth to go into orbit around another planet, and that showed us a very different kind of Mars, and I'll come back to that. And then it's succeeded by the Viking experiment, very ambitious, as you heard this morning, in which we were saying there's a paradigm that if life can exist anywhere on the planet, it exists everywhere on the planet. So that I can land, I can scoop up some soil, I don't need to be very particular about where I land, and I should be able to find out whether or not the planet has life. What did we find? Well, Mariner 4 showed us this, a very moon-like landscape on the planet. We shouldn't have been too surprised. In fact, papers have been written that we should expect craters on Mars. It was closer to the asteroid belt after all. The impact rate should be higher than for the moon. But we still had this mind of a thicker atmosphere that was screening out some of those impacts, making it less so. It was certainly a rugged planet. And as we got more examples of what it looked like, we still could see things that were saying, yes, it's not just a dead world. There are polar caps, for instance. And there are things like you see this ring feature in the middle of the lower right thing there, which those are clouds. And they could be orographically derived. Percival Lowell hadn't seen any mountains, either at the terminators or when they were seen on edge. And mountains would have been a bad thing for his canals, because canals would have to go up and over such things, and they didn't seem to do that in any particular way. But in reality, of course, there were some rather tall mountains on Mars. The great volcanoes that we've seen, that's the Viking image over there that shows you what we were indeed looking at when we saw these clouds around the rings. We didn't appreciate just how high these mountains might be. In fact, there were several people, Bruce Murray actually, in a debate prior to Mariner 9 going into orbit, said there are no mountains on Mars. Geologically, it doesn't seem to be a very active planet. And of course, Mariner 9 disproved that in a big way. But first, there was a global dust storm, similar to this one that was shown later in these Hubble images of the planet. And when Mariner 9 went into orbit, it couldn't see most of the surface except for 4 prominent dark spots, which turned out to be the summits of these very tall volcanoes rising high into the atmosphere. Well, Mariner 9 showed us not only had there been water active on the planet, but there must have been episodes of massive water activity. Streamlined islands in some of the big channels, massive canyons that were cut, and there are stream beds inside the canyons that have shown the changing positions. Furthermore, it showed that, for instance, in the polar caps were layered in a way that suggested ice ages and the progressive buildup and maybe tear down of these things. And that, of course, excited us about what the planet might have done in recent geologic time. If you needed more evidence that water had flowed on the surface, there were these valley networks. However, they weren't everywhere, and it suggested that there was a kind of episodic nature to the climate change on Mars. Well, all of that was good. The fact there was water, it was still on the planet. It hadn't completely desiccated, even though it might be much drier today than it had been in the past. When Viking went and landed on the surface, though, we were disappointed in that when we scooped up pieces of the soil, put it into the astrobiological instruments that were on Viking, we didn't get definitive evidence that there were any life forms. In fact, we couldn't find carbon in the material, which was strange in itself because there should have been inorganic carbon just from the infall of meteorites on the planet. So that suggested that the surface, in fact, could be a very hostile. There could be oxidizing agents that would break down the very compounds that were important to life as we knew it. Well, that gave us pause. A bigger pause was the fact that we changed the launch system for the human program again. And so we had our lost decade, and then we got back to exploration of Mars. There were some stumbles in doing that, but once we did, what we found, we got maps of the surface at resolutions that were unprecedented to all of planetary exploration. We also were able to do things like actually measure the topography, just how high was everything. Did those channels actually flow downstream, downhill? And we were able to do that. For a time, we actually had a better global topography map of Mars than we did for some regions of the Earth. Other things that we were finding was the presence of ice in the mid-latitudes, close to the surface. So one of the questions is, if Mars had all this water early, where did it go today? One thought was it had been lost to space. In fact, that was Percival Lowell's idea about planets just gradually lost water over time. The Earth would do that too. It was just behind Mars in that planetary evolution, because Mars, being smaller, was an older planet in his scheme. What we know now is that the other place that water can go and still be there to interact with the surface is in the near surface areas and stuff. So, evidence for past water activity on the ground and in the near surface. Phoenix dug down through a few centimeters of soil, exposed the ice. We know it is there. It's physically present. And we also found other things in the minerals that suggested there were reactions in chemistry that could go on that might explain some of those puzzling Viking results 2 decades earlier. So here's the litany of these spacecraft. And I'll point out again this idea about, in this case, there was a synergy between orbiters and landers. Viking actually pioneered it. The orbiters carried the landers into orbit, tried to find and scout out the landing sites for them. They didn't have much time to do that. And then the landers were released and went down to the surface. Well, now we do it by separate missions for the landers and for the orbiters, but they're still doing the same roles. Find the landing sites, find the interesting places on the planet, so that when we do land, we invest our time and effort in the right places, the places with the highest scientific potential. We also use the orbiters as relay communication satellites, which enormously increases the amount of data that we can return from the landers. And we're doing that at unprecedented levels today with Curiosity. And that's good, because if you count the number of cameras that mission has, they're quite a number. So, back to Mars, we started, and we introduced a new element, which was rovers and the ability to move about the surface. That's important for 2 reasons. The biggest one is that you don't want to have the frustration of seeing something interesting that's just beyond the reach of your robotic arm or whatever device you have that gets your instruments onto the surface or picks up soil samples from the surface to ingest into onboard laboratories. So that mobility was very important. I think Opportunity landing in Eagle Crater, that was very pronounced, because there it was, the exposed bedrock, right there in that small crater wall, and if it had been a fixed lander, it would never have been able to sample any of that. Of course, it was able to see that, and let me jump ahead here, and one of the things it saw were these blueberries that you heard about, which were hematite concretions. Hematite is a mineral that requires the presence of water to form. This was the first of several lines of evidence that said this area had seen the activity and presence of water, in fact, in repeated episodes as well. Still early in the planet's history, and how early was hard to determine from these alone. Let me back up for just a moment here to remind you about these global topography sets. Not only did we map out the topography of the planet, but the magnetic fields. Mars lost its magnetic field very early, but the fact that there are areas that are permanently magnetized even today says it must have been a very strong field, and the loss of that may be very much connected to the loss of some of that atmosphere that was there in early times. We also see evidence geologically. Whenever you see layers, that's a geologist's dream, because that's telling you here's a rock record of history that I can read. We also saw things like these gullies on the walls of craters and canyons, and that suggests that maybe the planet is still active even today. We answered one of those old mysteries about how things darken, because on Mars, it's the wind that does it, but just not any wind. Sometimes there are the dust devils. And you think, dust devils, a track or two across here? Well, in some cases, you get thousands of dust devils creating a cross. And then from space or from the Earth, what you're seeing is the gradual darkening of this vast region, all due to the action at a very local scale. Seasonally dependent, you bet. You don't get those kinds of things until the surface is hot enough to get that vertical motion and the spinning action of the dust devil. Opportunity is still looking, ground truthing things today. We see some more spherules here, but these aren't hematite. These are something different, which just goes to show that everything is not the same everywhere on this planet. We thought that for a time, that it would be very homogeneous. The wind sort of carries everything around, but it's a very thin veneer that the wind is distributing over the planet, and getting beneath that and seeing what the planet is made of is what has helped us understand its history. Polygonal ground, you bet there was ice in this ground at one time. Maybe it's still there, maybe it's not, maybe this is now desiccated. But look at the scale of this, it's very fractal. You go from the A to the B, you go down to something that's a football-sized field, and we actually see that there's even patterned grounds within that at the resolution of a few meters. That's what resolution can do for you. Well, we're in a new site now, Gale Crater, that was picked on the basis of this reconnaissance of the whole planet, finding the right sites to try to go to look for some place that could have been habitable. That is, the conditions could have been conducive to life. Now, whether or not they were, that's what we're trying to get to, down on the ground, and trying to understand whether or not the role of water that we think we interpret from space is actually one that occurred. But there are indeed layers, and they are exposed here, and they're not just, it isn't just the morphology of these, it's also the chemistry of these. Some of these are sulfates, some of these are clays. They're stratified, they're separated in time, suggesting that Mars' history has had different water environments over that time. And our question is, how global, how regional was that? So what are the lessons to take away? Mars is a complex planet. It has many different kinds of landforms. It has a cryosphere, it has the land, it has the surface layers, it has an active atmosphere. It also is a planet that is changing today. These are called regional slope lineae, which is our way of trying not to say we think they're brine flows on the planet. Because what you see is these darkening things occur only during certain seasons. In fact, when the ground is the warmest and a brine flow might be liquidized at that time and affecting on the place. Polar caps, they still change. In fact, we see a trend in which the South Pole cap may actually completely lose its CO2 cover in 100 years if that's not reversed by the natural processes. Sand dunes, we've now got a record long enough and with resolution key enough that we are able to see it actually moves. And of course, the big dust storms. Now, I want to just take a moment to address this question of novelty that was brought up. You know, major discoveries, right. Is there water in the atmosphere or not? That's kind of the stage we're at in many cases, certainly with exoplanets. You know, water in those atmospheres today. When you go to the next step, it isn't that you lose interest. The nature of the question changes, but it can be just as important. Take Earth as an example. We know there's ozone in the atmosphere. We know it changes, but we want to know why it changes. And because it's the Earth, we want to know whether or not we've got some part in that. The level of question gets more detailed, but the importance of the question is just as great as before. And in fact, we're still trying to get to that point of understanding whether there's life on the planet. All right. If I came back and wrote down, as I did here, why Mars today? Many of those questions are very much the same as what we saw before. No, we're not expecting intelligent beings. We're not expecting engineers to greet us, the engineers that built the canal system, because it's not there. But there is life. And there was a point made earlier about, yes, but if it's not a skeleton, if it's not people-like, is the public going to still be engaged in that? And I think what we've seen in the build-up to Curiosity says, you bet they are, because any kind of life form elsewhere, anywhere else besides Earth, is important for them. So the question that I'll leave you with is, will there be a third wave of Mars exploration involving humans and robots in different ways that we've done it before? To this point, the humans have all been back here on Earth, but still operating the vehicles far away. That may change with this third wave. Thank you. there are sort of two things that characterize the dark areas. One is they don't have dust, because that's the bright areas. And what makes a dark area dark and keep it dark, it tends to be a rougher surface. And you can think of many reasons for that. Some of the darkest areas on the planet, Syrtis Major, which is the most prominent of those, there's a huge volcanic complex. And that may be younger geologically, and that roughness is still there. And it's the roughness that actually stirs up the wind, which helps remove the dust after one of these global dust storms puts dust down and makes it brighter. So it is a combination of slope, roughness of the surface, and composition, in some cases, of the material.
Jason Callahan, you mentioned that the magnetosphere of Mars had dissipated early in its life, and that this might have resulted in the loss of the atmosphere, or parts of the atmosphere anyhow. What are the current theories on the cause of the dissipation of the magnetosphere?
It's a good question. One of the areas that we don't know very well is the interior processes of Mars. Fortunately, the Discovery program has just selected a mission that's going to put a seismometer down on the surface, put a heat flow experiment into the crust, which will help tell us about the models of that. One of the things I also didn't mention here is Mars has a dichotomy in its topography. The southern highlands, over which Mariner 4, 6, and 7 flew by, got most of their photographs, is a heavily cratered, high-altitude area. The northern areas, the northern plains, are relatively low in elevation and relatively smooth, looking like they've had a lot of debris that covers up that more cratered surface. All of those things could be related to the internal processes of mantle convection, plumes, hot spots, and then we also have the whole issue of the Tharsis volcanoes, those 3 giant volcanoes on the ridge in Olympus Mons, the solar system's biggest. How that develops. Was there a persistent hot spot? Think of Hawaii, where the islands aren't strung out, but they're all sitting in, that plume is just not moving. There's not much evidence of plate tectonics on Mars, and that seems to be one of the big differences in understanding its difference in the geologic evolution.
Yeah, just a quick comment on the dust and darkening and changes of albedo. In the telescopic days, the wave of darkening was always one of the stronger pieces of observational evidence. It did occur that might have been related to biological activity. And I've always found it interesting historically that Carl Sagan was one of the lead scientists in debunking the organic or plant life model for that in favor of moving dust around. He really followed the scientific method.
Exactly. The wave of darkening was the observation that there seemed to be this darkening of these features that occurred each spring, and it started, this wave of darkening started in the polar regions and seemed to sweep down into the lower latitudes. So, vegetation, wouldn't it be responding to spring just like it does on the Earth? And Jim Pollock and Carl Sagan picked up an idea that had actually been promulgated to say, well, the dark areas are really volcanic dust, and that's what's blowing around and changing with time. But they took it and showed that you didn't need a volcano to do that. And also, you could match the timing. The circulation would be that way to make it look like you were spreading the wave of darkening from the poles.
I apologize for a very provocative question, but I'm still asking you. Well, we have SNC meteorites on the Earth, just studied in detail in the labs, which are going to be confidently coming from Mars. Then why we need to undertake sample return mission? Do you think we will take something new?
The meteorites are an interesting set of samples. And the problem is we don't know their origins from the places on Mars. Where did that material come from? In fact, there's a whole cluster of many of them that are of similar age. So we're not getting a representative sample of all of the surface of Mars. So by knowing where we're going and taking those samples in the geologic context that we will observe when we collect them within these global data sets, that's the big difference. And that's the reason people have also suggested that we might just go to the moons of Mars and pick up material that has been blasted off of the surface. But that has the same problem. We don't know the provenance of those materials.
Our next speaker is David Grinspoon, who studies planetary evolution with a focus on habitability. David was previously at the Denver Museum of Nature and Science until yesterday, when he moved to Washington, D.C., to take up the first ever chairship of astrobiology at the Library of Congress. He's also the author of the award-winning book, Lonely Planets: The Natural Philosophy of Alien Life.
All right, thanks a lot, Janet, and thank you so much to the organizers for the ability to participate in this exciting anniversary party. I don't have slides, as Janet mentioned. I just yesterday finished driving across the country, and I don't know where any of my stuff or any of my materials are. But fortunately, this is a topic I've been thinking about for most of my life. So hopefully it's in here, and I do have some crib notes here. So the topic is evolving concepts of planetary habitability in the age of planetary exploration. And when I wrote the abstract, it wasn't actually specifically about Mars, but I've been shoehorned into a Mars session here, which is fine. I'm a big fan of Mars. And so I don't know if that means I should speak more about Mars or more about, or less about Mars, because a little bit of what I want to do is put Mars in the larger context of our thoughts about habitability. At any rate, the story begins, I think, between 4.5 and 4.6 billion years ago, when the Earth and its brethren and sistren accreted through a series of increasingly violent collisions, perhaps culminating with the moon-forming collision on the Earth. And then there were a smattering of waves of accretion that had quickly settled down and were pretty much all over by 4 billion years ago, setting the stage. And then things sort of bubbled and percolated and evolved along after that accretion. And then, perhaps somewhat mysteriously, about 50 years ago, something very strange started happening, a curious anti-accretion. And I mean curious in two senses of the word: curious, strange, and curious also because it was an event of an action of curiosity. Bits of the Earth started flinging back into the solar system from whence they had come. Small metallic objects filled with instruments orbiting back out into the solar system, heading for the other planets. Now, from the beginning, one of the motivating forces of this anti-accretion, this returning of some of the Earth back out into the solar system, has been the question of life elsewhere. As living beings and as a biosphere, we want to know, are we singular in some way, or are we commonplace? And even, in a sense, we are curious about curiosity itself. Is our quest, our ability to wonder about the rest of the universe extraordinary, or is it somehow inevitable, or both? Now, right now I'm hurtling through my 53rd orbit. So I'm just slightly older than planetary exploration. I have to confess I don't have direct memories of Mariner 2 from when I was 3 years old, but I do actually think I remember the Mariner 4 results being talked about in 1965. I definitely remember being excited about the appearance of the new Beatles record, Beatles 65, in 1965. And certainly, like all space scientists of my generation, the Apollo project launched me personally into space and set me on my current course. I, like many of you, I was also a science fiction freak from an early age, and as we gained the ability to send real machines into space, the excitement of participating in that enterprise eclipsed even the excitement of the fantasy space travels of Isaac Asimov and Arthur C. Clarke, although they all sort of merged together in my young imagination. At any rate, this golden anniversary that we're celebrating now provides an interesting opportunity to look back at our changing ideas about the limits of life and about the environments and natural history of planets and how they've changed throughout as a direct result of and during the time of planetary exploration. Planetary science as a field was born in response to planetary exploration and the need to forge a new multidisciplinary discipline that could handle this new data about the planets. It wasn't really a question about astronomy as traditionally practiced. In order to understand the planets, we needed the techniques and the insights of the earth sciences. So planetary science, in a sense, was born of a marriage between astronomy and earth sciences that was needed to scientifically respond to the opportunity to do planetary exploration. And just as another sort of personal observation in regards to that, when I went to grad school in the 1980s at Arizona, in a department of planetary science, none of my professors there had PhDs in planetary science, because when they were in grad school, there was no such thing. Now those same departments are filled with faculty that have degrees in planetary science. Similarly, the birth of astrobiology in the late 90s was sort of a marriage of convenience of planetary science with astrophysics as well, and biology, because we needed that approach, that combination of disciplines to deal with our growing sense that we were on the trail of life and our growing conviction that not only was that the motivation for planetary exploration, but we could now admit that it was the motivation for planetary exploration. Exobiology, of course, has existed since the beginning of planetary exploration, but it was a little bit more fringy. And NASA shied away from completely embracing it as the raison d'etre of planetary exploration until the late 90s, when some scientific developments happened which increased our confidence that this was really a worthwhile and solid endeavor, and that the public excitement about and the public support engendered from embracing the search for life was greater than the negative impact that was felt previously of the sort of ridicule factor that in some ways was the legacy of the Lowellian stain that took a while to erase. And I think that the birth of astrobiology was in response, can almost be boiled down to a response to 4 developments. And in my notes, the 4 developments are simply outlined as the Mars rock, Galileo at Europa, extremophiles, and exoplanets. And I could explicate those further, but given that we don't have that much time and that I think you all know what I'm talking about, perhaps I won't. But at least 2 of those developments, the Mars rock, of course, ALH 84001, and the discovery of very good, compelling evidence for an ocean on Europa, a likely or certainly potential, perhaps likely habitat on Europa, both of those were direct results of planetary exploration. And the extremophiles and the exoplanets are a little bit less directly related to planetary exploration per se, but certainly important in the founding of astrobiology as a field that's central to NASA's mission. Astrobiology is fundamentally about the relationship between planets and life. And so in thinking back over these 50 years and wondering where we're going, it's interesting to note that I believe actually, in a certain sense, our ideas about life have actually changed very little over these 50 years. And it's our knowledge of planets that has changed a lot. And I'll be a little bit more specific what I mean about that in a second. One of the things I love to do is read outdated books of popular science written by scientists and see what they knew or what they thought they knew and compare it to what we know or what we think we know now. One of my favorite writers in this genre is George Gamow. I have a copy of a book he wrote called Biography of the Earth, that came out in 1947, and its cover price is 35 cents, which gives you, little context on what else has changed in these decades. And it's stunning when you read that book, both what they knew and what they didn't know compared to now. For instance, they had had the insight that the Earth is very old and that you could determine that through radiometric dating. However, the age of the Earth is confidently given in Gamlov's book as 2 billion years old. So they had the principle right, but they didn't quite have the decay constants and the math right. The origin of the moon, of course, you know, the moon had broken off from the Earth and the Pacific Ring of Fire and all that, like we were taught in grade school. And there was no plate tectonics, but there is a section in that book about essentially exobiology. He does speculate on finding life on the other planets. And remember, this is 1947. And what he says is basically, he doesn't use this exact phrase, but what he says is follow the water. And so in that sense, our basic idea about how to look for life hasn't changed all that much. Well, in 1953, the structure of DNA was deciphered, and at that point, I will submit to you, we knew as much about life as we know now. Not really in the details. If you're a microbiologist, you're sitting here getting mad at me. But what I mean is we had the fundamental knowledge that we use now to look for life elsewhere. We knew that life was water in organics. And that's the sophistication of what we bring with us as we search for habitable environments elsewhere. So what's really changed is what we've learned about planets. At the dawn of the space age, both Venus and Mars were regarded by many scientists as pretty good habitats for life. As Rich Zurek outlined, there were some doubts at the beginning of Mars exploration, but the idea that there could be plant life on Mars was still taken seriously, and the idea that Venus might be a watery world, there were some cracks in that view because of radio astronomy, but when our first missions left for the planets, it was still there was still a lot of optimism. And in fact, in 1959, Miller and Urey of the famous Miller-Urey experiment wrote an article in Science magazine talking about that it's quite possible that we will find DNA-based life on Venus and Mars and what we could learn from that. And of course, there's that famous paper in '61 that Carl Sagan wrote on the eve of Venus exploration talking about summarizing current thought about Venus, saying that it may be a carboniferous swamp, a windswept desert, a planetary oil field, or a global seltzer ocean. And that's a classic paper if you haven't read it, Science, 1961, Carl Sagan. But certainly, it wasn't outlandish. There could be life, our kind of life, on the surface of either of those planets. So the early results of the first interplanetary probes were very disappointing in that regard. Our naive optimism, perhaps naive optimism, was dashed by those first results about learning how alien those planets really were. New York Times editorial in February 1963 commenting on the results of Mariner 2 that was entitled, "Venus Says No." And it talked about, this marks the end of the beginning of mankind's great romantic dreams, and said, quote, "Mars now remains our only hope of turning this universal dream into reality." Well, 2.5 years later, the New York Times had an editorial commenting on the Mariner 4 results in July 1965, and that editorial was simply called "The Dead Planet." So there was a lot of disappointment at first in response to perhaps our naive optimism. Both neighboring planets turned out to be a lot less Earth-like in terms of surface environments that had been imagined by those planetary astronomers who inferred oceans on Venus and seasonal plant life on Mars. But optimism and wishful thinking reign supreme in this field, and they will not be dissuaded by data. Life was pushed off the surface of Venus and Mars and into the past of Venus and Mars. But in the subsurface of Mars, and maybe even in the clouds of Venus, and certainly in the glorious past, life still remains on those planets. For both Venus and Mars, we actually have reason to believe that each started out much more Earth-like, and there was a fall from grace. At least this is the story we tell ourselves and think we can support with evidence. So I have a list of 6 stages in our views of habitability at least in our solar system. 1, naive optimism. 2, initial disappointment. 3, resurgent optimism, visions of past life, resilient life, which is really what Viking was based on, and non-surface life. Now, Viking was motivated by and perhaps helped to quash this wave of resurgent optimism. But also we've had evolving ideas about the habitable zone. And the habitable zone, which was actually really first discussed quantitatively by Su-Shu Huang in the early 60s, has become much more sophisticated now, and we realize it's not just a function of stellar distance, it's also a function of planetary evolution and size. If you swapped Mars and Venus, they might both be habitable. Mars's problem is not necessarily that it's too far from the sun, but it's too small. It's lost its activity and its atmosphere. So if you swap Mars and Venus, we might have 3 habitable planets. So, and then finally, of course, beyond the inner solar system, right, Heidi? We've learned a lot that's changed our ideas about habitability. And then finally, the exoplanet revolution. Let's see, how much do I have? Okay, 5 minutes. So during these same decades, our knowledge of Earth and the evolution and diversity of terrestrial life was also rapidly changing due to developments such as plate tectonics, which was in the early 60s still kind of a radical idea. By the end of the 60s, widely accepted as our unifying view of terrestrial evolution. And the plate tectonics led to the birth of Earth system science, which I think now we're trying to generalize to planetary system science. And a couple ideas that I think are worth mentioning are the formulation and debate of the Gaia hypothesis. As checkered a career of the Gaia, as the Gaia hypothesis has, and as much abused as it has been, I think it also represents an essential insight about life that's very important as we think about the relationship between life and planets potentially elsewhere. That is, the biosphere is an integral part of the Earth, the inseparability of the living and, quote, non-living parts of the Earth, and life is something that, in a sense, happens to a planet, not just something that happens on a planet. And a related idea that I have advanced that I'll just plug here for a second is something I call the living worlds hypothesis, which draws attention to the fact that life on Earth enjoys the benefits of residing at the intersection of 2 great heat engines, the internal one and the external one, both of which are very active. And I have suggested that for the long-term existence of a biosphere, this may be as important as simply the presence of liquid water. And the only other place we know in our solar system that shares that attribute, perhaps, is Titan. There was the, of course, the Chicxulub impact that really brought home to us a relationship between evolution of life on Earth and the rest of the solar system. It wasn't just an abstract concept. The rare earth hypothesis, which I regard as fundamentally wrong-headed, I have a paragraph here which I won't take the time to read why that is, but if you want to ask me, you can. Of course, the discovery of the numerous extremophile metabolisms and habitats, which have greatly expanded the range of watery physical conditions. Extremophiles discoveries have taught us that water is not only necessary, but seemingly perhaps sufficient for life, at least on a planet like ours, that it's remarkably coincident, the range of life and the range of liquid water. And finally, almost finally, I want to get to the outer solar system, that detailed reconnaissance of the outer solar system, beginning with Voyager and continuing with these later missions, has really expanded our notions of habitability, because we've learned about the existence of gravitational habitable zones, which do not depend on proximity to any kind of star, and in fact, who knows, may define the largest amount of habitable real estate in the universe. Finally, more recently, the discovery of a complex methane hydrosphere, or methosphere, on Titan, and a likely subsurface aquifer on Enceladus, along with a rapidly expanding catalog of exoplanets, has stimulated new ideas on the range and detectability of planetary habitability. And we're even thinking a little bit more about life beyond water. It's being taken a little more seriously now because of the methane, liquid methane cycle on Titan, combined with the existence of complex organics and copious energy sources. There are some very clever chemists that are working on this problem and sort of pushing us again to question of whether our water bias is intellectually valid or just a parochialism based on the experience and environments of Earth. I wanted to say, I'm almost done, I wanted to say just a couple things about Venus, because I submitted an abstract that was just about Venus that was rejected from this meeting, which is fine. but especially having been shoehorned into a Mars session here, I'm aware of what might be called a little bit of myopia, although it might be a useful myopia. I believe in exploring Mars, and I believe there are good reasons to explore Mars first, although partly we may be searching under the streetlights for our keys, because Mars is certainly much easier to explore. But just a couple quick points about Venus, that its close proximity to Earth and similarity in bulk properties suggests an almost controlled experiment with heliocentric existence in the presence of life as the two main variables. Yet major differences in their evolutionary paths have caused us to reevaluate our models of terrestrial evolution. Certainly, if we want to know the limits of a habitable zone around Alpha Centauri b, which people want to know now, the best way, I would submit, is to send new missions to Venus. And certainly if we want to know the future of life on Earth-like planets around Sun-like stars, we had better send new missions to Venus. I was very encouraged by Jim's chart showing that there are some big Venus missions at least on the chart, if not nearing the launch pad right now. If Curiosity finds signs of life on Mars, in a strange way it will confirm our views of the origin of life. It doesn't really revolutionize scientifically our view, it confirms it. When we find those conglomerates in Gale Crater, we're confirming what we thought, that there was running water there. It's very exciting to find, but it's interesting to me that in a certain sense that if we make that tremendous discovery, it's more a confirmation than a refutation of our current sort of naturalistic worldview about life and what it takes. In conclusion, astrobiology is about the relationship between planets and life. Today, we are more sophisticated about planets than we are about life. We're beginning to learn about the diversity of planets. We know nothing about the diversity of life. In another 50 years, I expect that we will. Thank you.
Thanks so much. About 5 minutes for questions.
That was really great. I wanted to poke at something that you said earlier in your talk that would appear to be at conflict with something that you said later on. You made the observation about life existing at the interface between external and internal heat sources. And yet we think about Europa, it doesn't really have an external, it's internal. And Titan almost the same way. And yet your later statement was these may be the most prevalent habitable zones in the universe. Can you expand on that? And
yeah, certainly. Very good point. You know, I think that when we look around the universe and we try to derive criteria for what might make a habitable environment, we're very susceptible to the danger, or we're in danger of just looking for ourselves out there and for reaching the conclusion that, you know, the Panglossian conclusion, this is the best of all possible worlds. We just have to look for a place with conditions just like this. And it may be true, but it may not be true. So it's interesting to say, well, okay, obviously Earth has a climate conducive to liquid water on the surface, and that's one set of criteria. What else is it about the Earth that's unusual that could also possibly differentiate habitable planets from non-habitable planets? And it is striking the level of ongoing geological and meteorological activity on Earth, and certainly life, the more we learn about life and you know, the way it fits into Earth system science, it takes advantage of that. It's not just a coincidence. So that's really my point, is that, that's something unusual about Earth, and for all we know, it may be true of all habitable planets. And in that sense, I'm intrigued by the fact that Titan shares that. Now, Europa is an interesting case, and maybe is a test of this hypothesis. If all you need is liquid water and organics and energy sources, Europa ought to have life. But in a certain sense, you know, if you sort of, what I'm calling the living worlds hypothesis, if you generalize it to you need ongoing internally driven geologic activity that is feeding this sort of cyclic exchange of matter and energy that life feeds off of, then I think you could argue that Europa shares those, although maybe that this intersection of two heat engines is specifically relevant for surface life. obviously, I'm still working on the idea. Maybe we should have a beer later and, and refine this, yeah.
Oh, this is information, you probably know it well. I've had a long relationship with the Museum of Science in Baltimore. I've lectured there many times. And they're opening an exobiology exhibit sponsored by NASA. I'm sure you knew that. That'll be on the 1st of November. I've been invited as a donor, but you'll never guess what I loaned them. They wanted a pristine first edition copy of The War of the Worlds. That's good exobiology, isn't it?
Excellent, excellent. Well, I think it's a great choice. If for no other reason than the first page of The War of the World is one of the finest pieces of Western literature that exists, and even that sort of crappy remake of that movie with what's his name in it, the beginning of it was wonderful because it had the voiceover directly reading from that first page, which is it's worth just watching that scene. Yeah.
Okay. Thank you.
I seem to remember there was an instrument on Curiosity that would help characterize the source of methane that's been seen. Have we gotten any recent news from that?
That's a great question. Curiosity should be able to resolve the methane issue. And when I mentioned the recurring existence of wishful thinking in interpretations of data from Mars, I was thinking, for instance, about the publication in the 1960s of in Science magazine of the spectral signature of chlorophyll on Mars, which later turned out to be deuterium in Earth's atmosphere. And it may turn out that these methane observations historically fit into that pantheon of optimistic interpretations. We don't know yet. It's controversial, and there's some very smart people who are very critical of the methane interpretation, and some other very smart people are sure that it's true. And it's exciting that Curiosity has that ability in the SAM instrument to look for very minute quantities of methane. And methane is a leaky substance, and the Curiosity team is large, and there have been some hints that maybe some people know the answer to this question. And I was during Jim Green's talk, I was trying to read his lips very carefully, but nothing has been officially released. But I wouldn't be surprised if sometime this year there was an announcement about that.
Thank you very much. Thanks, David. Great. Our third